Hi everyone, so today we are looking at the addition of hydrochloric acid to propene. So we've already discussed adding hydrochloric acid and water to other alkenes, okay, but they were symmetrical alkenes. They had nothing but hydrogen surrounding them. So we are looking at asymmetrical alkenes, or those that have substituent groups. And our substituent group today is a methyl group, and we can see that guy here. Okay. And this will basically present us with a choice in our next step. So we'll dive into it straight away and we can discuss these things as we approach them. So this reaction begins as all our other reactions do. We identify the source of our electrons first. So we have some pi electrons here in our double bond. And we have electrons surrounding our chlorines and our hydrogens. Okay, so hydrogen has one electron here, and that is shared in a polar covalent bond with chlorine. And we know that chlorine has 7 electrons in its outermost valence, indicated by the blue dots here. We know that chlorine is more electronegative than hydrogen, so it's going to pull the electrons closer to itself, and when it does that, we indicate it with a delta negative sign, meaning it's electronegative or more electronegative in this bond, and that makes hydrogen more electropositive. And this becomes important later on, okay? So just remember that. So what's going to happen is these pi electrons are going to bump into or interact with this hydrogen at some point, and they're going to bring it over to itself, okay? Now, hydrogen can only have one bond, so the bond between the hydrogen and the chlorine must break. And when it breaks, this red electron is going to be pulled towards the more electronegative chlorine, okay? And we'll see that now shortly. This hydrogen has a choice as to which carbon on either side of the double bond it can go to. So we're going to draw out both possibilities first, okay? So we go from a double bond to a single bond, and we can either end up with either one of these options. Okay, so we can end up that it goes to the carbon on the left with the most hydrogens. And actually what I'll do here, I'll pop this new hydrogen in red just so we can keep track of it. And if we do that, this carbon on the right ends up as our carbocation, and that would get a positive charge. Or we could have it on this side, and the carbon on the right becomes our carbocation, so it gets its positive charge here. And we get our new hydrogen popping over here on the right. Now, you have already discussed this and come across this in your lectures, so you know already that you are going to be thinking of the Markovnikov rule. And the Markovnikov rule will tell you that the hydrogen is going to add to the carbon with the greatest number of hydrogens, okay, to produce the most stable carbocation. So we already know, and we can see it very clearly, that the carbon that has the most hydrogens is the one on the left. Okay, so when we add our hydrogen to the one on the left, we generate what is known as a secondary carbocation. I'm going to write that out here. A secondary, carbocation. And it's a secondary carbocation because our cation here is bound to 2 other carbons. So 2 other carbons around it, directly bound to that carbon, make it a secondary carbon. Whereas this carbocation here is only bound to 1 other carbon. And that makes that a primary carbocation. And if we had a carbon bound to 3 other carbon groups, then we'd have a tertiary. And basically, the more carbon groups you have around it, the more stable it is, the more energetically favourable that product is. So, between our secondary carbocation and our primary carbocation, our secondary carbocation is the most stable. And that's the one that's going to form. Okay? And so there's no confusion. It's this one in the big red box that is going forward in our next step, okay? So if we were to do this in the lab, we would see at the end that we should have our our secondary carbocation, or a product made from our secondary carbocation, that will be most or in the highest proportion. Okay, so we bring this up here. Now, so we've already identified now that our secondary carbocation is the most energetically favourable to be made. We brought forward now in a reaction, and we can draw this out. Identifying our carbocation, keeping our hydrogen red there just to make things easier for us. And now we bring back our chlorine. And remember, our chlorine had, let's pop them in blue. Chlorine had 7 of its own valence electrons originally, but because it was so electronegative, when it broke the bond with hydrogen, it stole the hydrogen's electron, so it's gained a negative charge, and a formal negative charge. Okay? And this is going to interact with the positively charged carbocation. A bond is going to be formed, and what we will end up with now is our actual product. So what we end up with is that we have our chlorine popping here. We have our hydrogen that we borrowed earlier popping in here. And this, okay, so we're going to name it. So we have, that should be, that guy should be CH3 group. So we have 3 carbons in a line, okay, our longest carbon chain, so we already know we're dealing with something with prop in the name. Our chlorine is on carbon number 2, no matter what way you go about it. So this is going to become 2-chloro-propane. That is the product that we have made. If we look at it all together, we can see that we started from our propene. We identified the source of our electrons anywhere we could. We looked at the electropositivity and the electronegativity of anything that was relevant. We showed the movement of electrons with our curly arrows. We introduced our Markovnikov rule, which is really, really important here. And we identified where the Markovnikov rule states that our hydrogen will go. So we know that our hydrogen will add to the carbon with the greatest number of hydrogens to produce the most stable carbocation. The most stable carbocation will be the one that has the most carbons bonded directly to your carbon with the positive charge. So in this case, it's your secondary carbocation that has 2 carbons directly bound to it. And that's in comparison to your primary carbocation that only has 1 carbon directly bound to your positively charged carbon. And then that very stable, or that more stable, secondary carbocation will interact with the chlorine that now has a negative or a formal negative charge to form our final product, which is 2-chloropropane. So as always, give it a go yourself, write them out and try and explain it out loud. And any questions that you may have, you can leave them in the Moodle forum. Okay?